problem. If you want to write that on the back, one side, I don't know what the front back is, but 12 ounce can pop. Yep, yep. Forgot to write. Yeah, what are you doing? Like on time.
I know, right?
It's crazy.
Okay.
Did you shave your video?
Hey.
Yeah. That's good. So we're gonna start to use statistics to make decisions, yes or no, instead of like estimating an interval. So Pepsi says there's 12 ounces of pop in a can. I don't know if you guys have seen this in the news lately. Like Doritos give you like 4 less chips than they used to. What was one of them? Like a Captain Crunch, I think I read. There's like a couple ounces less. So like if you think about that as a company, you put 4 Doritos less in every single bag you make. Trillions of bags. It adds up. So it wouldn't surprise me if a 12 ounce can of Pepsi is really like 11.8 or something. They claim it's 12 ounces in a can. We suspect they're lying. We take an SRS, sample size of 30, and we get 11. With a standard deviation of 2. But I only took 30 samples. So we're either going to call them a liar or we're not. There's nothing I can do to prove that it's actually 12, but I can try to prove that it's less than 12, or I can say, yeah, it's probably not less than 12. Similar to innocent and guilty. Like if you go to trial, you don't get proven innocent, right? You either get proven guilty or declared guilty or not guilty. Like no one ever at a trial says the verdict is innocent. It's either you're guilty or not guilty. I can't really prove you're innocent, but I can't really say you're guilty. So that's kind of this idea. We're going to be able to say, yeah, you're lying, or yeah, you're probably not lying. But we can't ever say, yes, 12 is the precise thing unless we do like all the data. So let's say that they claim 12, and let's say this was 11.99. So you took a sample size of 30 random cans, there's billions of cans, comes out to 11.99. Would you feel comfortable calling them a liar at that point? I would not. What if it was like 8 ounces? Obviously, you're a freaking liar. 11? Like I kind of lean towards yes, but I'm not sure. So there's got to be some way to like make a decision, right? Like a cutoff point. So that's what we're gonna do. All right. So flip it over, and this is like the confidence intervals. The first time I go through this, you're gonna be like, "What are you talking about? I don't understand it." Just like trust process, right? All right. So t-test. That's what we're doing. We're doing tests now instead of intervals because we're testing to try to make a decision. T, does T deal with means or proportions? T is means, and the proportions are DC. Okay, so you're gonna say H sub 0, U equals 12. It's called the null hypothesis. Trust the process. Big 2 letters in it. What the hell? So this is called the null hypothesis. I'm trying to like do some little note with the null. That's like the original claim. Null hypothesis. So the null hypothesis is like if everything is how it should be. That's what we're at. And then you get this HA. It's the alternative hypothesis. And so our assumption or guess or claim, whatever you want to say, do we think the actual mean is bigger than 12, less than 12, or just not 12? We think it's less than. We think they're trying to save a little bit of money, right? So mu is less than 12. This is like our default starting position. Like we can't just assume they're wrong. We just look at that's what they said. That's the null hypothesis. That's what everything's based on. But we have this alternative idea where we think they're lying, and we think that the true mean is actually 12. So this is our setup. They're telling us it's 12. Okay, fine, we'll go with that for now. We think they're liars. I put in a bunch of data, did some sampling, and then see that. Conditions, the exact same as you were doing before. Everybody remember him? So SRS is stated. Did I say SRS?
Yes.
So SRS stated. Remember, the population standard deviation is unknown. If I knew the population standard deviation, I would have all the data, and I could just look to see what the true average is. Like I wouldn't need to run a test at all. What else was there? Independence. So is 30 less than or equal to 10% of all Pepsi cans? I think they've made a few more than 300 Pepsi cans. And then the fourth one, we are going to be using a T distribution. To make sure that's okay. So there's three ways that can happen. Remember? Yeah. Population standard deviation, or population is normal, and is greater than or equal to 30. And if you don't have either of those, what do you gotta do? You gotta do like a dot plot, but that's pretty rare. We have n is greater than or equal to 30 here, so we're okay. This part makes more sense after we talked about it a little bit, like the top part. Okay. Alright, now we're doing the math box. So this is now a different formula. This is test statistic equals statistic minus parameter over standard deviation of statistic. And if you remember with confidence intervals, we had like the one formula, but we applied it to 4 different situations. It's the same thing here. This is your general formula for running a hypothesis test. And then we'll plug it into 1 sample T, 2 sample T, 1 proportion, and 2 proportions. So 4 different things. So in this one, with T, we're just doing 1 mean. What's the statistic in this situation? Or what? Yeah, X bar. Minus, what's the parameter? Mu. So if you remember, statistic comes from the sample, and then parameter comes from the population. So X bar is like what we got, it's our 11, that's what we got. Mu is 12, we said mu was 12 up here, so we're just going to plug it in. And then the standard deviation is the standard deviation of X bar divided by the square root of N. Same thing it was before. Wait, can you see that? You have glasses, like you're good?
Yeah, I think so.
I don't know if you're being sarcastic.
I can see.
Okay. But that wasn't like an unreasonable question.
No, it wasn't.
Would you like to stop talking now? Okay. What's X bar in this situation? 11. What's mu? What's S sub X bar? 2, is that what I said? And then the square root of N? So the square root of 30. Alright, get your calculator out. already have it in, but you should see this. Remember, there's like, do you have a list of the data like in your L1? We don't. Or do you have statistics? We do. So mu sub 0 is whatever mu was for h sub 0. It's like the initial assumption. So that's 12. X bar is 11. That's our sample. Standard deviation is 2. Sample size is 30. And then you get these three different options here. You choose the same direction as you wrote on your paper. So like we have mu as less than 12, right? Or like the arrow's pointing to the left. So you want the arrow to be pointing to the left here also. And then I'm gonna hit calculate for now. We'll draw it eventually, but right now I just want to make sure you get that t and the p value. So make sure your two numbers match mine. They don't, let me know so we can figure out what's going on. Yours don't. Anybody else? We're good? Okay, so then so go back to here, and this is what we just calculated, the negative 2.74. Let me draw it. We'll kind of talk about a little bit of what is going on. So the I'm doing the same thing. I'm just hitting draw instead of calculate. I guess that yours says arrow when it goes to draw it. We'll figure it out. No, you don't need it right now. This is actually pretty useless. Well, let me just like kind of talk about what we're going for. So, you don't worry about drawing. If you can't draw it, we'll fix it later. Okay. So this right here is 12. That's what they claimed. What this is telling us is our sample was negative 2.7 standard deviations below that. So we're like way over here. So we're in this area here. This P is the probability, this is a hard concept. P is the probability that if this is true, if their claim is actually true. Pepsi is straight up with us, they're putting 10, 12 ounces in every single can, or they're doing the best they can to put 12 ounces in every single can. If that's true, this is the probability that we would get something this far away from 12 in our sample. That's a really small probability, right? Let me say it again. This number, the 0.0052, super small number. It's called your p-value. Trust process. If they're not lying to us, if they're telling us the truth, you're gonna get like some cans are gonna have 12.1, 12.2, 11.8, 11.9. Like there'll be some fluctuation, right? It's probably not just 12 every single time. There's probably like a little bit of wiggle room. If they're telling the truth, that like little bit of error or wiggle room would give us a result this far away from the middle, that percent of the time. So what that tells me, like the further away I get, what am I more likely to think they're lying or not? If I go further this way, am I more likely to think they're lying? Yes. So the further, like if I took a sample and I got here, like 11.9 and t equals like negative 0.05 or something, like I'm very, very close. That would result in a p-value of like 0.45 or something. The further away you go, the further this way you go, the more likely it is that we're going to call them a lie. Let's think of, okay. We're going to try to just think of it a different way. How fast do you throw? throws 89 miles an hour. Well, do you throw 89 miles an hour every single day? Like, there's fluctuation, right? Some days it's a little bigger, some days it's less. You can think about this with like running times, swimming times, anything, a lot of things. So I go watch Connor pitch, and I'm like, oh, he throws 89. I'm fired up. This will be fun. And I go watch him pitch, and he's this many standard deviations below. He's at 81. What do I think about his claim of 89? Probably a lot. If it was 75, is he more likely to be lying or less? More likely to be lying. So the further we are away, the more likely we're going to call the original claim a lie. Right? Be like runners. Yeah, Trent, what's your 400? 54 seconds for a 400. Trent's bragging about this all day. He's like, come see me. Do it in 54 seconds. This is the opposite way, though. So I go watch it, and it takes him a minute 30. What do I think about his claim? I think his claim sucks. So I think he's probably lying, right? So that's like the idea that we're trying to get into. Let me go back to that paper. Okay. Okay. Write this down. Exactly know what it is. Trust the process. One of those things. So you're gonna go TCDF. Remember normal CDF? Use that. Or some of us use the table. So TCDF, we're gonna go negative 999, negative 2.74, and then we always, if we're using T, have to tell the calculator the degrees of freedom. How many degrees of freedom are there in this problem? 29. I'm trying to get that. That minus 1. It's one less than the sample size. So if I do, so go second dister. What should I say? Second bars. And then number 6 is TCDF. So I'm just typing in this. I actually already know this number because it was on the graph. But sometimes they won't. You won't have enough information to run the test, so you'll have to be able to do it this way. So you put that in. There's that 0.0052. We already saw that, right? We already got to do it. But I'm just showing you how to get to it a different way. Alright, the very beginning of the problem, well, okay, so we're going to write this to equals p value. So this is basically the probability that it's not quite this simple, but it's similar to the probability they're telling the truth. So this is the probability they're telling the truth. What do we do? So we're going to make a little sketch, and then we're going to do conclusion. We went around a room on one page. So we're going to kind of sketch what they had on that thing there. So this is 12. That's our middle. And then over here, I'm going to put alpha equals 0.05. I gave you that back here. And the problem, this is what we use to make our decision. So that's kind of like our cutoff point. So anything to this side of that is in the rejection zone. So 0.05 means there's like 0.05 area over here. Like the size of this is 0.05. First day back. I like this. Okay. Kind of run out of room here, but do this. So go t equals. Again, I know this is like way overwhelming. We will go through all this. T equals inverse t 0.05 comma 29. Type that in and see if you get negative 1.7. That's in second bars as well. The inverse t. Why'd I put 29? Here's your freedom. We good? You with me so far? With me-ish. I know it's a lot. Alright. Their t value is negative 1.7. Our t value was negative 2.74. Are we in the rejection zone? This is 1.7 standard deviations below the mean. Right? That's what I thought. We're 2.7 standard deviations below the mean. Are we in the rejection zone? Alright. So we're over there somewhere. So, because of that, that's the rejection zone. We're going to reject H0. We are officially saying we think they're lying. Because we're in the rejection zone. If we were like here, if t was like negative 1, I would not be able to reject their claim. So that's the cutoff point. Which side of that line are you on? Right. So I am going to reject. So I'm going to say that since p value is less than alpha, not only did I teach you something that is crap load of overwhelming, I just tell you like 2 different ways. I understand this is a ton, is what I'm saying. We will break it all down. Since p value is less than alpha, we reject H times. There is enough evidence to reject HO. We suspect HA is true. So I did that a little bit weird, and again, I know this is hard, but I went with, you can compare T or you can compare P values. I like showed you comparing T's, but I wrote the P values. This is what you're comparing to, these two things. So if this P value is less than this alpha, you're going to reject, you're going to call it. Or if the T value is like in the rejection zone, you're going to call it liars. Kind of get to either way. But what this is saying is that I reject H naught. I don't think this is true. I have enough evidence to suspect that this is true, which means I'm calling Pepsi a bunch of liars. I'm not getting afraid to say questions. Are there questions I can answer? Like, it might be so overwhelming you don't have questions yet. Or is there anything that you can think of that I can discuss right now? Yeah.
Does the alpha apply to the other side?
It would if I was like doing a greater than, like if I thought it was above. So that it depends on which one you're doing. And if it's not equal to, it's on both sides. Anything else I can try to address right now? Alright, read it up. Connor, can I use your fastball velocity?
Perfectly fine with me.
Alright. Wait, that's like okay.
Yeah.
So I'm I suspect he's a liar. I don't actually. So I take an SRS of 40 pitches. I find out that X bar is 87.5. The standard deviation is 3. I don't know if I'm going to lie there. I don't think so. I don't think I'm lying. Oh no, I was just thinking of that. Let's say alpha equals 0.10 this time. We're going to change it a little bit. So there's the problem. That's the situation we're presented with. That's what we're going to work with. And so, like before, when we were doing confidence intervals, I would have said, like, make a 95% confidence interval for how fast counting grows. It would be like 85 to 94. But this is more like, do we think he's telling the truth or not? I'll flip it over. Are we good? You guys have this written down? T-test. I'm going to do mu first this time. That makes more sense. Mu equals true population mean velocity for right. HO is the null hypothesis. That's like I assume that everything as it should be, and like I'm not. I think he's telling the truth. I'm just going to start with that fact. So my H0 is that mu equals 89. HA is what we suspect might be going on. So if I think he might be lying, I think his velocity is actually maybe less than 89. That's kind of my initial start. That's not up there. That's like your thesis statement. That's like what we're trying to do. I'm looking for true population, the true velocity. He says 89. I think it's less. That's all that's saying. Conditions are the same as it ever was. So SRS was stated. Independence would be like 40 is less than or equal to 10% of all the pitches he's ever thrown. He's thrown more than 400 pitches in your life. Population standard deviation unknown. And then T distribution, why am I allowed to use a T distribution here? Say it is greater than 30. N is greater than or equal to 30. Calculus cuss word. Okay. Test statistic equals statistic minus parameter over the standard deviation of the statistic. That is the formula for every single test. And then we just start plugging in like our specific scenario. So is our test statistic T or Z? T? Why? How do we know? That's what Molly said. Why do I say that? Why? I said why the T and Bud said because that's what Molly said. So I was asking you why you said that. Q. T or Z, and you go with Q. So it's like you just pick someone else. It's T because we're dealing with means, right? If it was proportions, it would be Z. So basically, because of that word, it's T. I was thinking of those guys. So what's our statistic in this scenario? Our like actual statistic. X bar. Parameter is mu. Standard deviation is S of the square root of n. This is the same as the prior unit. Like I'll make a cheat sheet for you, and as long as you do all the qualifications for the, check marks, you'll get to use each on the test. If you don't, you don't get cheat sheet. I think it'd be really bad. What's X bar in our current scenario here? 87.5 mu. Right? Because that's what we stated up here. Like that's what that was the initial claim. Standard deviation was 3, and then 40. So we're going to find out how many standard deviations we are above or below the mean. If we are a lot of standard deviations below the mean, what do we think of this claim? If we're very far below the middle, what do we think of this claim? It's a lie. If we're close to his middle, wait, what's cap? Truth or lie? Cap is a lie. If we're far away, if we're a large number of standard deviations below the mean, this claim is cap. Did I say that right? So go to stat. Stat. Tests. 2. What's up? It's a lot of standard deviations, guys. So like I can tell right away, that's pretty far below the mean. 3 standard deviations is a long ways. So I'm gonna say he's capping. Capping. Alright, now I gotta do my TCDF. So go ahead and type that in, and basically you're making sure that you get the p-value that the test just showed you. So I get that. So again, that's second bars. Number 6 is the TCDF. So we could call it, instead of the rejection zone, we could call it the cap zone. Why? Where this come from? Why is cap? Alright. To make my diagram here, so 89 goes in the middle. Here I'm going to put my alpha. It was 0.10, remember? And I need to find the t that goes with that. So that is inverse t 0.10, comma 39. 39 is like 1 less than n, right? anything on this side of it is in the cap zone. No, you need the TCF. Who's in it? Okay. So our T value is negative 3.16. So the cap zone cutoff is 1.3 standard deviations below the mean.
Oh, so
We're 3.16 standard deviations below the mean. So are we in the cap zone? Yeah. So we cap it. So somewhere over here is like his actual value. Another way you can look at that instead of like is it in the cap zone or not, compare this number to 0.10. Is the 0.0015 less than 0.10? It is. So we're gonna reject. Sorry, I tried to make you like okay. So since p value is less than alpha, I wanted to do one that didn't reject so you guys can see one of each, but I screwed up. Okay. We reject HO. There is enough evidence to support. So just think about this. If I'm rejecting HO, then what is there enough evidence to support? If I'm saying that's wrong, I must be saying I think HA is okay, right? So there is enough evidence to support HA. We suspect HA is true. I think it's. I'm saying he's counting. Did that get a little bad the second time? Still probably like